Welcome back. In the last session, I just explained about PLL, the block diagram of PLL, and then I explained how the crystal oscillator clock is acting as a reference and giving you the stability at the output of your LC circuit because of negative feedback. The negative feedback is taking care of correcting the resonant frequency from your VCO. If there is any variation in VCO, the negative feedback is the one which is what is correcting it. Therefore, and then ultimately it is what is stabilizing to your F0. But the core of the PLL is nothing but VCO. That is what we had seen. Now let's see the problems. You may expect at least one question out of 2 sets or 3 sets from regulators. They are important. Okay. Classroom work problems. From chapter number 4. Okay. Write down problem number 19. We had seen already 18 problems. We had seen already 18 problems, right? From classroom workbook problems. Problem number 19. Tell me, the configuration of the figure is, this is straightforward, right? But what it may be, for the sake of completeness of the problem, let me draw. Therefore, the circuit is this is ground, R1, R2, okay, and this is RC, this is RC, and this is ground, this is RC, RC, right? This is your output, let us say. Tell me what is this? I told you, right, wherever there is series RC and parallel RC, you can think about Wien bridge oscillator, right? Yes, this is Wien bridge oscillator. This is nothing but open loop amplifier, and this is nothing but beta network, right? Series RC, parallel RC, that output is going to your amplifier input. This is Wien bridge oscillator. What is the answer? Option A, precision integrator. Option B, Hartley oscillator. Option C, Butterworth high pass filter. Option D, Wien bridge oscillator. What is the answer? This is Wien bridge oscillator. This is Wien bridge oscillator because this is what is your beta network. This is your beta network, and this is what is your open loop amplifier, right? This is your open loop amplifier A. What it may be, this is Wien bridge oscillator. Wien bridge oscillator. What is the answer? Answer is D. Done. Now problem number 20. The circuit in the figure employs positive feedback and is intended to generate sinusoidal oscillation. If at a frequency f0
beta of f is equal to Vf of f by V naught of f is equal to 1 by 6 at an angle 0. Then to get sustained oscillation at this frequency. Okay. Now problem number 20. Problem number 20. The block diagram is given. What is the block diagram? This is nothing but minus plus
This is your beta of f. Okay. Then this is the output. This is the output. Okay. This is your output. This is V naught of f. Okay. Now this is plus minus whatever it may be, and this is what is feedback quantity Vf of f. Okay. Now this is R2 R1. Now this is what is the block diagram given, and saying that it is employing positive feedback and it is intended to generate sinusoidal oscillation, asking for sinusoidal oscillation. And we know that if you observe clearly, right, and he has given beta of f at f is equal to f naught, let us say that is resonant frequency, at f is equal to f naught, given that the beta of f, which is the feedback quantity Vf of f divided by V naught of f. This is already given, which is 1 by 6 at an angle 0 degrees. Therefore, what does it mean? This is nothing but your beta network. This is your beta network having 0 degrees phase shift. It is nothing but your beta network. And where is your open loop amplifier? Actually, this is what your open loop amplifier. This is your open loop amplifier A, right? Then, saying that your beta network is giving 0 degrees phase shift, then your open loop amplifier also should give 0 degrees phase shift. Then you will get total loop phase shift 0 degrees. Yes, this is nothing but non-inverting amplifier which will give you 0 degrees phase shift, because input is at plus and then output we are taking directly. Okay, that is what is given to beta network. Therefore, this is what is giving 0 degrees phase shift. But now he is asking for to get sustained oscillations, right? He already told that it is giving you oscillations and that oscillation frequency is also f naught. But now he is saying at that frequency to get sustained oscillations, what is the condition? Option A, R2 is equal to 5 R1, option B, R2 is equal to 6 R1, option C, R2 is equal to R1 by 6 and R2 is equal to R1 by 5. Okay, we know that to get sustained oscillations, what is that? Your total loop gain must be equal to 1. Therefore, your A beta is equal to 1. Therefore, what is your A? 1 by beta. Therefore, what is beta? Beta is already given 1 by 6. Therefore, it is 6 at an angle 0. Therefore, your open loop gain should give angle 0 at an angle 0 degrees. Therefore, what is mod A? Magnitude should be equal to 6. And what is the open loop gain? That is nothing but non-inverting amplifier. We know that A is equal to 1 plus R2 divided by R1. R2 divided by R1. Therefore 1 plus R2 by R1 should be equal to 6. Then only you will get sustained oscillations, because you will get A beta is equal to 1. Then what is this? R2 by R1 is equal to 6 minus 1, 5. Then what is R2? R2 is equal to 5 times of R1. If R2 is equal to 5 times of R1, you will get sustained oscillations. Okay, that is what is from Barkhausen criteria. Second point. The first point is already given. It is giving you oscillations at f naught. This is giving 0 degrees phase shift. This is also giving 0 degrees phase shift. You will get oscillations. But now the second point, to get sustained oscillations,
the total loop gain must be equal to unity. Therefore, what is the condition for R1 and R2 such that you will get sustained oscillations? What is the answer? Answer is A. Answer is A. We are going to get sustained oscillations. After that, problem number 21. If that is over, problem number 21. I'll give you 30 seconds time that we will see problem number 21. The people who have completed, they can look for problem number 21. We'll see the solution. Done? Okay. Now 21. The oscillator circuit shown in figure is Hartley oscillator with some oscillation, Colpitt's oscillator with oscillation, Hartley oscillator with oscillation, Colpitt's oscillator with oscillation. Even though you don't know completely about the circuit, but we can say the answer. Split inductor, Hartley oscillator, split capacitor, Colpitt's oscillator, right? And we know the frequency also 1 by 2 pi root over LC. That depends on L equivalent or C equivalent, that depends on whether it is Hartley or Colpitt's. Straightforward. Even the open loop amplifier, which is what is given, doesn't matter, but you can take it. Okay. The circuit is, this is problem number 21. The circuit is, this is what your inductor, RF inductor, this is minus VCC and this is LC. Okay. Now, this is what your PNP transistor. This is what is having inductor, and now this is having capacitors. Now this is what is having, this is your output voltage V0. Okay, then your input is having biasing for the amplifier, then there is a capacitor, and this is what you are again biasing. This is Q point stability, this is for Q point stability. Therefore all are grounded. This is CE and this is RE, this is R2. These values are not given because not required to solve this problem. CC, they are used such that it is in active region, therefore it will act as an amplifier, and Q point is stable, therefore only for amplifier. At resonant frequency you should give the gain whatever you need. The gain requirement is very less. That's what I told, right? Okay, L is given, L is equal to 10 microhenry, and this is connected to this, which is ground basically. C1 is 2 picofarad and C2 is equal to 2 picofarad. And asking for type of oscillator and F0. We have 4 options. Okay, this is GATE 2000. This is for 1 mark. Okay, whatever it may be. Therefore, this is nothing but split capacitor, right? C1, C2 with ground. Therefore, what is this oscillator? This is basically Colpitt's oscillator. Because this is nothing but your beta network, right? Therefore, this is nothing but your Colpitt's oscillator. When I say this is Colpitt's oscillator, right? What is the frequency of oscillation? F0 is equal to, again I am saying, if I wrote before, which is root over 2 pi LC, that is wrong. You have to write 2 pi root LC, okay? L into equivalent capacitance CEQ. Therefore, what is that? Which is given 1 by 2 pi. What is L? L is given as 10 microhenry. 10 micro into what is C equivalent? We need to calculate, right? Therefore, what is C equivalent? 2 into 2. Therefore, equivalent capacitance. C equivalent capacitance is equal to C1, C2 divided by C1 plus C2. They are in series. Then, what is that? It is nothing but 1 picofarad. When you calculate, you will get it. It's like resistors in parallel. What it will be? Therefore, now this is 1 pico square root. Therefore, what is this? If you see the answers, okay, we need to calculate everything. 1 by 2 pi into 10 micro into pico. Pico is 10 to the power of, what is pico? 10 to the power of minus 12 and 10 to the power minus 6. 10 to the power of minus 18. Then this is nothing but root over 10 into 10 to the power of minus 18. It will become 10 to the power of minus 9. The 10 to the power of minus 9 will become 10 to the power of 9 divided by 2 pi root 10. Approximately, if you see here, this is nothing but less than 1 gigahertz. You have any answer nearer to 1 gigahertz? We don't know. We need to calculate. Let's see. What is pi? 3.14. And what is root 10? Approximately 3. 3 into 3, 9. Approximately 10. 10 into 2, 20. 1 by 20, 0.05 gig. Nearer to 50 megahertz. Therefore, this is nearer to 50 megahertz. The answer which is nearer to 50 megahertz, that you can choose. What is the answer? 50.3. Answer is B, Colpitts oscillator and 50.3 megahertz. Therefore, answer is B, right? Colpitts and 50.3. Answer is B. Okay? But exact answer, if you use calculator, you will get it. But approximately, you can do it. Okay? Because if you see the options, right? The options are having some delta, not too much. Let us say 50.1, 50.2, 50.3 megahertz and all. Then we need to use calculator. Else we can go with some approximation and then get nearer value. Okay? That is what is your answer. Answer B. That is what is your Colpitts oscillator. Okay? Done? Okay. Now write down problem number 22. Match the following. Match the following. List 1, Hartley, and then Weinbridge oscillator, crystal oscillator. List 2, let's see. Okay. Match the following. List 1. Option A, Hartley. Option B, Weinbridge. Option C, theoretical problems or qualitative problems. Crystal. Okay. List 2. 1, low frequency oscillator. Low frequency oscillator. 2, high frequency oscillator. High frequency oscillator. 3, stable frequency oscillator. Stable frequency oscillator. 4, relaxation oscillator. Relaxation oscillator. 5 negative resistance oscillator. Negative resistance oscillator. Okay. Now let's see. Whatever you know, try to map. Okay. Now Hartley oscillator. What is Hartley oscillator? Surely I can say, and before that, low frequency oscillator, low frequency of oscillations. High frequency of oscillator or high frequency oscillator, high frequency of oscillations. Stable frequency oscillator, we know. But did you hear what is relaxation oscillator? Actually the name of relaxation oscillator, right? That is coming from UJT, right? This is nothing but UJT oscillator, sawtooth waveform generator or whatever may be, therefore UJT oscillator. This is not required. Negative resistance oscillator. Negative resistance oscillator, it's like tunnel diode, using tunnel diode or gun diode for microwave. And I can say UJT oscillator, your UJT is also having that, therefore your UJT oscillator. All will exhibit negative resistance. But because of negative resistance, why do we get oscillations? Just a small point, if you take tank circuit, what is tank circuit? That is nothing but your LC circuit. Your L and an inductor, capacitor. Split inductor, Hartley oscillator. Split capacitor, Hartley Colpitts capacitor, Colpitts oscillator. Anything is fine. Therefore now, let us say this is L, this is C. You take this capacitor, charge this capacitor, having some voltage. Now take this capacitor, keep it here, close the switch and then leave it. You know what will happen? Whatever energy the capacitor is storing, that energy will be going to inductor, and again the inductor, whatever it is storing to some point, again it will it will give the energy to capacitor. Therefore there is interchange of energy between inductor to capacitor. That is what is by means of a frequency component, which is nothing but sine wave. The energy transfer is by means of sine wave. But remember, if there is no loss of energy, then definitely it will give you it will continuously give you oscillations without dying out. But practically your inductor is having some resistance, right? When energy transfer due to current flow, then if there is I square R losses, then whatever energy which you have given initially, then that will be like dissipated slowly through inductor resistance or capacitor ESR, then ultimately those will be died out. It is exactly same as simple pendulum. You take simple pendulum, right, and you take a ball which is winded with a rope, and the rope is exactly fix it to one tip of your stand of your simple pendulum. Then take the simple pendulum ball, give some energy. I am giving energy, leave it. Therefore we give potential energy, and the capacitor energy is potential energy. The inductor is energy is nothing but kinetic energy. Mechanically, whatever we have seen, right, potential energy, kinetic energy. Remember, potential energy is associated with position or level with respect to Earth's surface. Due to gravitational force, it has m into g into h. H is nothing but height from the Earth's surface. That is what is going to create potential energy. And dynamic energy or kinetic energy is associated with dynamic nature. If it is having a velocity or it is traveling, if a body is traveling, right, definitely it will have kinetic energy, and that is nothing but half mv square. Capacity is the one which is what is storing the charge, therefore storing the electric field by means of electric field, therefore it is storing the energy, electrical energy. Therefore now there is no charge movement, but it is storing the energy. It is like a potential energy. Now if there is a charge movement and then storing the energy, there is a current, the current is producing magnetic field, that magnetic field is trying to establish such that it is going to store the energy by means of magnetic field in the case of inductor, because that inductor is opposing the incoming current by means of magnetic field, whatever may be, it is storing the energy. Therefore both are reactive elements. When this is storing, it will act as an active element. Once this is delivering and this is acting as a load, then this is acting as an active element. Therefore both are acting as reactive elements, but both will not deliver at the same time. Once capacitor delivers, inductor takes. Once inductor delivers, capacitor takes. Because of that reciprocal concept between inductor and capacitor, it is what is storing and then giving the energy. Same as mechanical experiment. Take a simple pendulum, give potential energy, that is what I told, right? Take a capacitor, charge it, now potential energy or energy stored by electric field, give it and then loop. give some potential energy, leave it. What will happen? The potential energy whatever you have due to gravitational force, it will be converted to dynamic energy or kinetic energy. Then it will have velocity. Now potential energy is minimum, but kinetic energy is maximum. The tangential velocity is maximum to the simple pendulum. Again it will go up. It is opposing the potential energy. It is opposing gravitational force and the gaining potential energy. Your kinetic energy is becoming zero. Again it will go back. Therefore the energy, the total energy is constant. The total energy is constant, but the total energy is equal to kinetic energy plus potential energy. Therefore, when potential energy is decreasing, kinetic energy is increasing. When kinetic energy is decreasing, potential energy is increasing. If you take a thread and an environment, if there is a loss, there is an opposition, if there is some loss of energy, whatever I gave initially, then slowly your simple pendulum oscillations, right? They will slowly, what will happen? They will die and then it will come back to zero. If there is no friction in the tip, and there is no opposition by the media or the air, which is what is there in the simple pendulum experiment, then it will always oscillate. Therefore continuously it will oscillate without any loss. We don't need extra energy. Therefore if there is any loss by your simple pendulum experiment, no need to give extra energy, it will continuously oscillate. Exactly the same way if you take your tank circuit, right? Definitely because of your resistance component of your wire or inductor or capacitor ESR, there is a loss of energy. If there is a loss of energy, how much is the loss of energy? We need to provide with some external source or external amplifier. That external amplifier has to provide that much energy in sync to the energy whatever it is losing. That is what is maintaining closed loop phase shift is zero. That is what is qualitatively maintaining 0 degrees phase shift. Therefore having positive feedback, whatever energy which is what is lost by your beta network, that much energy should be provided by your open loop amplifier. That is nothing but sustained oscillations, which is nothing but closed loop gain A beta is equal to 1. Therefore the system which is what is having closed loop gain is equal to 1 at resonant frequency, that is what is going to give you sustained oscillations or critically damped oscillations, right? Therefore this is what your tank circuit. Now why I am explaining, both are opposite elements, that is why it is storing the energy. Kinetic energy, potential energy, both are opposite energies, right? Therefore these two are opposite elements. Similarly, equivalently with the negative resistance. What is negative resistance? Negative resistance in mathematics is not negative resistor. Equivalently people represent it as negative resistor. Therefore what is negative resistance? Actually if voltage is increasing, whatever current you have, the current will decrease, something like this. If voltage is increasing, your current will decrease. This is what people say negative resistance region. But it is not negative resistor. Physically there is no negative resistor, but this is negative resistance region. Therefore what is it doing or what will it do? It is like reciprocal. We have a resistor, effectively a resistor, and if you have a negative resistor, let us say, can I say both are reciprocal elements? If you can create reciprocal concept in a circuit, that will give you oscillations. Therefore, if you have a positive impedance or positive resistance or the positive whatever it may be, exactly opposite to it, which is nothing but reciprocal, which is nothing but negative resistance region or negative resistance operation, then remember you will get oscillations. Why? If this is what is delivering the energy, it will take the energy. When this is delivering the energy, it will take the energy. Only the direction of the energy, that is what is defining. Once it takes, it will deliver. Once it is delivering, it will take, or something else will take. Therefore, because of that, because of reciprocity, energy transfer will happen from one point to another point. If energy transfer is happening from one element to another element due to reciprocal elements, then you will get oscillations. Exactly something like your tank circuit. That's why if you take a tunnel diode or gun diode or UJT oscillator, they exhibit negative resistance region along with positive resistance, then you will get oscillations. But there is an amplifier inside. Whatever loss you have in the beta network, while having the reciprocity or while having the energy transfer from one point to another point, there is a loss. If there is a loss, that much loss should be provided by your amplifier from DC power supply. Therefore, that will be done by your amplifier. I hope this is clear. These two are not associated to the oscillators, whatever we had seen, right? Now, we can map. You know everything, right? Hartley oscillator, high frequency oscillator. Greenbridge oscillator, with respect to Hartley, it is low frequency oscillator. Crystal oscillator, it is stable frequency oscillator. Therefore, what is the answer? A is mapped to 2, B is mapped to 1, C is mapped to 3. That is what is the answer. Okay? Take it. Sometimes we can solve the problems qualitatively. We don't need any quantitative analysis. Okay? These are all known to you, but I am just trying to correlate with respect to other concepts and other aspects. Therefore, it is easy to understand and remember. That will increase your analysis skills. Qualitative analysis is always powerful, remember. But we need quantitative analysis to get the answers and all. But remember, both are required. But out of these two, if you ask me which one is easy to understand and then decode in a better way, or understand a circuit in a better way, always qualitative analysis is the one. Okay. Try to understand qualitatively, but try to derive quantitatively. Combine both of them and try to match. If both are matched with respect to the analysis, then you can go ahead. Forward, but anyway, for the sake of solving the problems and to understand or to apply the theory what we understood, we are solving. Okay, but we have student workbook problems that you try. Anyway, you are going to solve, but you try before seeing the solutions. Can you erase? Okay. Problem number 23. The value of C required for sinusoidal oscillations of frequency 1 kHz in the circuit of the figure is. Problem number 23. Circuit is, we want oscillations, therefore we call it as F0. Therefore we need F0 is equal to 1 kHz. If we want F0 is equal to 1 kHz, then this is 1 kilo ohm and this is 2.1 kilo ohm. This is V out. Okay. Then asking for what is the value of C. What is the value of C to get F0 is equal to 1 kHz. Therefore, to get frequency of oscillations 1 kHz, the value of C, that is what is asking. Option A 1 by 2 pi microfarad. Option B 2 pi microfarad. Option C 1 by 2 pi root 6 microfarad. Straightforward. Okay. Option D 2 pi root 6 microfarad. Okay. Okay. Tell me what is this oscillator? This is nothing but your Wien bridge oscillator, right? Wherever you have series RC, parallel RC, that is your beta network. Okay, we already derived. That is nothing but your Wien bridge oscillator. When I say this is your Wien bridge oscillator, what is the frequency of oscillations? Therefore, this is Wien bridge oscillator. Wien bridge oscillator. We know that what is the resonant frequency? F0 is equal to 1 by 2 pi what? RC. There is no root 6. That root 6 is there for RC phase shift oscillator. Don't confuse. Okay. Now, tell me, we know F0 is equal to 1 kHz, right? Now, R is known to you. We need to find C. Therefore, what is C? Therefore, C is equal to 1 by 2 pi F0 into R. Therefore, tell me 1 by 2 pi. What is F0? 1 kHz. R 1 kilo ohm. Therefore, what is this? 1 by 2 pi 1k 1 mega. It will become 1 by 2 pi microfarad. This is what is the value. Okay. Therefore, 1 by 2 pi microfarad. What is the answer? Answer is A. Answer is A. This is the answer. Done? Okay. One more observation. Tell me, this is Wien-Bridge oscillator. Yes, this is Wien-Bridge oscillator. But this is nothing but your open loop amplifier. This is your open loop amplifier. And this is your beta network. This is your beta network, right? This is beta network. And this is your open loop amplifier. Tell me, for your Wien-Bridge oscillator, right, what is the beta? When you calculate, what do you get? We got beta what? We got beta 1 by 3. Then I get to get sustained oscillations, right? Practically, right? Then what is A beta should be equal to 1, then A is equal to 3, right? That is what I told. Then what is A here? 1 plus R2 by R1. Therefore, what is A? Therefore, here A is 1 plus R2 by R1. What is that? 1 plus R2. What is R2? 2.1K divided by R1. 1K. Then what is this? 2.1. It is 3.1. Therefore, overall, what is your A beta? Your A beta is greater than or approximately equal to? Greater than or approximately equal to 1. Because what is beta? Beta is 1 by 3. Then 3, then A into beta. 1 by 3 into 3.1. It is slightly greater than 1. That's what I told, right? Practically, A beta will be taken slightly greater than 1. This is intentional. Don't think that it is wrong. This is correct only. Because I told you, right? Whatever noise which is what is coupled, the noise amplitude, whatever you have, that will be restored at resonant frequency. But I don't want to restore only noise frequency, whatever you have. Right? I want to boost the signal. Therefore, if you have A beta slightly greater than 1, you'll get whatever noise which is what is picked up, and whatever F0 it is picked up from noise signal, that is not only restored, that will be boosting or having over damped oscillations. But remember, as the signal level is increasing, then it is entering into non-linearity. Your op amp will have some non-linearity. The non-linear gain will decrease than your small signal gain. Then your A beta will be settled almost to 1. Let us say if that is not settled, the high frequency or not small signal, large signal gain is also same as small signal gain, then it will be touched to plus VCC minus VCC. Then we can do some other mechanism to control the swing at higher frequency or for higher voltages and all. Okay, that I think there is a problem that we will see. Then we will understand that. Okay, but this is also one of the ways. But practically, people take A beta slightly greater than 1, but close to 1. Slightly greater than 1. Don't take like greater than 1 means 2, 3. No, if you take it, you'll get clipped version of your sine wave, which is nothing but distorted sine wave, or I can say almost square wave, you'll get it. Okay, we want sine wave oscillations. If you want sine wave oscillations, then we should not see any clipping, right? We need clean frequency component from your sinusoidal oscillation. Okay, with this I can say it is done. Therefore, you can take it practically. This is what people take. Therefore, this is practical consideration. This is practical consideration to have over damped oscillations, from noise input signal, right? But as the signal level increases due to non-linearity, then the overall gain, large signal gain of your op amp will be decreasing. Then it will come to close to 1. Okay, it will be limited to that. Okay, I'll stop now. The session can be closed now. We will continue in the next session. From next session onwards, we will see the next topic, regulators or power supplies. Okay, you can take it. Therefore, we can close. Thank you. We will continue in the next session.